Hello friends, welcome back to my channel. So in previous chapters we have seen how we can do alkylation using different enolates, or how we can do specific alkylation and specific generation of specific enolates, and we have also seen that how we can do a Michael addition reaction. Michael addition reaction is basically when we are using enamines and enolates as a nucleophile for the substrate alpha beta unsaturated carbonyls. Right, so we have seen all these reactions, and we have also discussed about what is the basic aldol reaction. Next question comes stereoselective aldol reaction. Stereoselective means when you have this type of ketone, then there are two possibility. When you are using a base, there are two possibility that either you can generate a cis enolate or you can generate a trans enolate. Cis enolate means, suppose I am using LDA, so this is my cis enolate, these two groups on the same side. We will have to check about the OLI group, right? Oxygen containing group, that is, it is on the same side of bulkier group present on the second side, on second carbon atom of double bond. If they are on the same side, then it is cis. If they are on the different side, then it is trans enolate. Right, and when we are using two different type of enolates, there are possibility that we will get different type of aldol after reaction. So when I am using this aldehyde, this enolate will add to this aldehyde, and after addition it can give me two type of products. There are two possible products. This one is called as syn product. Syn means this OH is formed from this CO, right? After shifting of this bond, this O minus will take H plus and it will form OH, right? So when this OH and this R double prime group on the same side, this is R double prime group, when they are on the same side, it will give me syn product, and when they are on the opposite side, it will give me anti product, right? And cis enolate give us syn aldol product, and trans enolate anti-aldol product, and it is decided on the basis of a 6-member cyclic chair-like structure, and this model is called as Zimmermann-Trexler model. We will not go in the detail of this model. We have to simply remember the outcome of this, that cis enolate will give us syn aldol product and trans enolate will give us anti-aldol product. Right, then comes to this example in which we are using LDA and we have here R group. So we know that we can have either cis aldol product, or you should say in the starting that it can give me cis enolate or it can give me trans enolate. Cis enolate means this one is trans enolate, right? And this group R decides whether we will get cis enolate or we will get trans enolate, because ultimately the formation of syn aldol or trans aldol depends upon the type of enolate we have, right? And this enolate, which type of enolate we will have, depends on the group present here, right? When we have a bulkier group, when R is equal to a bulkier group like tertiary butyl group, then we will primarily get cis enolate. So if you have cis is to trans ratio, and when you are using tertiary butyl group, then this cis will be greater than 98% and this trans will be less than 2%. And when you have this R, a ethyl group or a smaller size group, then your cis product will be lesser. Why? Because if I have suppose a tertiary butyl group here, then this bulkier group can show clash with this methyl group present at in the trans position, because actually this group is like this tertiary butyl group, it can show clash with this methyl group, right? So it preferentially occupies cis position in which it is not showing clash with this tertiary butyl group. That is why when we have this bulkier group, it will preferentially give us cis enolate. Next is boron mediated aldol condensation. This is also a very important thing, that when we are using boron reagents, then which type of enolate we will get using different type of boron reagents. So again, this boron reagent will give cis enolate, or it can give me, this one is cis because this group and this methyl group present here are on the same side. This carbon can have hydrogen and methyl group, and out of these two, this methyl is bulkier, and this carbon has this OBr2 group, and here we have a ethyl group, and out of this we have to check that we will give priority to this oxygen containing group, right? So this is my cis enolate and this one is trans. So there are two conditions for when we will get trans enolate and when we will get cis enolate. So first we will take trans enolate when we have bulkier group in our boron reagent. We are not talking about R group attached here, right? In case of LDA, we have checked the alkyl group attached with our carbonyl, but when we are using boron mediated reagents, then we have to check the reagents attached with boron group, right? We will not check the methyl or any other alkyl group attached here. So we are talking about the bulkiness of our boron group. So when we have bulkier boron groups, like when the ligands attached with our boron are bulkier, like cyclohexyl group, means when we have bulkier ligand, we should say that our first condition is when we have bulkier ligand. Second condition is when our reagent has a poor leaving group like chlorine. And third condition is when we are using a unhindered tertiary amine, because for this reaction, when we are using boron when we want to generate boron enolates, we need some boron reagents like this one, right? As well as we need a base. We generally use tertiary amine base when we are using boron reagents, and when we have unhindered tertiary amine base like triethylamine, then we will preferentially get trans enolate. So these three conditions. Second, we will take the conditions for cis enolate. So first condition will be reverse of it. When we are using a smaller size group, means less bulkier ligands are used, then we will get cis enolate. Means if I am using, suppose, butyl group, in butyl group it is less bulkier, or you can say that it is smaller ligand, cis enolate. Second condition is leaving group should be good in nature, like triflate. Third is when I am using hindered base, hindered tertiary amines are used, like diisopropyl ethylamine, then it will give me cis enolate, right? So you can remember conditions for one, then just reverse it, then you will get cis enolate. These are the conditions when we are using normal boranes. But if we are using thioesters and boron mediated aldol condensations, we cannot apply these conditions, right? Because in this case we are using a smaller size ligand, butyl group, and we are using a hindered tertiary amine base. So I will get preferentially cis enolate according to these conditions. But because this sulfur can show chelation with our ligands, that is why it will give me trans enolate. Trans enolate means it will give me anti-aldol product. If I am using a aldehyde here, then it will give me anti product, right? Similarly, in this case I am using a bulkier group here, 9-ppn, and triflate. Triflate is a good leaving group, but 9-ppn is bigger in size, but the shape is such like that. The shape is like this. So these groups are away from this boron, that is why it will not cause hindrance, right? So that is why we will not include B9-ppn in bulkier size group. We have also discussed this thing in Claydon book summary, that we will not include 9-ppn in bulkier size group because of the position of these groups, right? And here we have a good leaving group, and base is again hindered in nature, but this time I'm getting cis enolate, right? And it will give me syn aldol. We can remember the conditions for normal ketonic groups. These are the conditions, but in case of thioesters the conditions are different, right? We cannot predict it easily. Then what about titanium enolate and tin enolate? So these two enolates will preferentially give syn aldol product. So you can remember this thing, that these two will give syn aldol product. And how we can generate titanium enolate? We need TiCl4 and some base like triethylamine. And in case of tin enolate, we can use tin triflate. We have also discussed about this in previous chapter, and amine base, right? Using these conditions we can generate these enolates, but important thing is these enolates will lead to the formation of syn aldol. This is very important. So out of all these things in this slide, you can remember this point, this is important, and this one. Then we will move on to chiral centers in carbonyl compounds. So when we have a carbonyl compounds containing chiral center, then what about the product? So we have discussed about it in detailed way in Claydon book summary, where I have told you that what is Falcon-Ahern model, and using this model we can predict the stereo selectivity of final aldol. You can use that model, or you can use Cram's model, which is not given in Claydon book, but I have made a video on this Cram's model, so you can use that one also. So here I have a enolate, right? And here I have a aldehyde group, and in this aldehyde I have a alpha chiral center, means on alpha carbon I have a chiral center. So according to Falcon-Ahern model, I can write down it like this, that this is suppose my carbon 1, this is 2, and I am looking suppose from this side. When I am looking from this side, the carbon 1 is like this dot, this 1, and the second carbon is like this outer circle. So according to this model, first I have to draw this carbonyl group as such, right? Second thing is, the bulkier group present on second carbon should be placed perpendicularly like this. Second group means you can say that this is the largest size group, this is medium size group, and this is a smaller group, and this medium size group should be placed like this, and the smallest size group should be close to this proton. These conditions give me smallest energy configuration, right? We have discussed in Claydon book summary that we can have different type of projections, but we have to select the lowest energy projection for this Falcon-Ahern model. Next question comes that from which side my nucleophile means this enolate will attack. It will always attack at Burgee-Donet's angle, means it will not attack at any angle. There is a definite angle at which attacks, and this angle is nearly 107 degree at which attacks, right? So, and it will try to attach from this side because it is not hindered side. We have a smaller size group here, but if it attacks from this side, this will be this phenyl group can cause hindrance. That is why it will not attack from this side. It will attack from the side of this smaller size group. So when it attacks here, it will attach with this carbon, and this bond will shift here, right? It will form OH. So we can also write it like this. We will place this pH as such, and this nucleophile will attach on this carbon. It is just anti to this one. These two groups will be on our side. This OH will go like this. It is attached with this carbon, and this methyl, which is attached with second carbon, will be placed like this. And here I have one proton. This one is second. right? Now what is the way of writing these groups? That these two are anti to each other, so I can write them like this. This is my second carbon, this one is first on which this nucleophile attaches. So these two are anti to each other, and the groups which are on the above side will be placed above the plane. They will go above the plane, and the groups on the below side will go below the plane, right? So this methyl and OH will go above the plane. OH is attaches with this nucleophile, so it is above the plane, and this methyl is also above the plane. Then these two protons are like this. Now if you want to rotate these carbons, you can rotate them easily, right? If you have any doubt about rotation, you can see my previous videos on this Falkenhayn model or Kram's model, or you can ask me in the comment section, I will tell you. Then next and the second important thing about this chapter is asymmetric synthesis with enolates and enamines. So if you have studied or asymmetric synthesis previously, or you have seen my video on asymmetric synthesis, then this part is very easier for you. Otherwise you will have some problems. So I would suggest you that first you watch my videos on asymmetric synthesis, or you can study from any other source, then you can watch this part, right? So when we want to do asymmetric synthesis, we can use different things, that we can use chiral pool, we can cause asymmetric induction using catalysts which are already asymmetric in nature, means they have some chiral centers already present in them, or we can use chiral auxiliary. So in this part we are talking about chiral auxiliary. Chiral auxiliaries are the group which generate chiral center in a group which is taking part in a reaction, and after reaction the chiral auxiliaries are removed, and these chiral auxiliaries are formed from a chiral compound, and they look entirely different from the compound from which we have synthesized them. So we are not talking about how we can synthesize these chiral auxiliaries here, but if you have any doubt, as I have told you earlier, that you can watch my video on them. But here we are using two chiral auxiliaries. These are Evans chiral auxiliary. Evans is a scientist which worked a lot in this field, in asymmetric synthesis and in chiral auxiliary field. And these two chiral auxiliaries are oxazolidinone auxiliaries. So we will come to the point how we can use it. Actually, the attachment site of an incoming group will be decided on the basis of the group attached here, right? If it is above the plane, then incoming group will go on the opposite side, right? In this case it is below the plane, so the incoming group will attach above the plane. Let's see that here we have a carbonyl group and we are using LDA here. So first we have to generate a enolate, or I can simply write down it like that, we have a negative charge here. Secondly, this negative charge will attack on this carbon and Br will be removed, right? This section is very simple. The question comes that what will be the attachment side of this allylic group. So if this group is below the plane, this allylic group will attach above the plane like this one, right? And we can easily remove these auxiliaries. We will see how we will remove them. Similarly, in this case, suppose I am using again the same conditions, but this time these two groups, methyl and phenyl groups, are above the plane, so this allylic group will go below the plane. Means in final product I will have. Next question comes how we can remove these auxiliaries. That I have told you that we can use alkoxides for their removal. We can use other reactions also to remove them. That we can use LiAlH4, then it will be converted into alcohol, right? And then we can use other oxidizing agents, so alcohols will be converted into aldehyde. So we will see that reactions a little bit later. First we come to the alpha alkylation of alpha amino acid. So in this reaction, first we are using a aldehyde, right? in presence of a protonic acid. So we will try to write down this mechanism of this reaction. So we have in the starting aldehyde, and we are using a protonic acid. So suppose it is attaches with this OH, so this carbon will become more electrophilic in nature, right? And this nitrogen having lone pair of electron can attack on this carbon. So this bond will shift here, so this whole group will attach with this nitrogen. And as this carboxylic group is above the plane, so suppose this tertiary butyl group, a bulkier group, tries to find a place which is less hindered, so it will go below the plane. In next step, there is transfer of proton from this nitrogen to this carboxylic acid group. Then this OH will attack on this carbon. This bond will shift here, and when it comes back, this OH2 group will be removed. So because this carboxylic group was above the plane, so hydrogen attached here will go below the plane. Now we have two 5-member ring fused together, and the proton attached here is below the plane. So the group, these two ring will be like this, right? These two group, it should have a open book like structure, and proton is on the below side, right? So we will see what is the use of this concept. So next we are using LDA. So this LDA will remove this proton and it will generate a enolate. So although the stereochemistry of this carbon is lost when we are generating a enolate, but still this methyl group, when we are shifting this bond here, this methyl group will attach from the side away from the cavity, because these two ring has a structure like this, so a group will not attack from this side, it is not possible. So methyl group will attach from the below side, right? So in final structure, this methyl group will attach on below the plane side, right? Next, if we are doing its acidic hydrolysis, so this water will attack on this carbon, this bond will shift here, and when it will come back, this ring will break, right? And this O will take proton from this acidic water and it will form OH. Next is again a proton will attack on this nitrogen and it will form, right? And finally this bond will break and we will have this one as final product. So ultimately what we have do, we have attached this methyl group on this carbon. This is alpha alkylation of alpha amino acid, right? So this is very lengthy way. Another possibility of doing this reaction is use of chiral auxiliary. So this is our chiral auxiliary, and in this reaction we are using LHMDS. So this lithium hexamethyl disilazane will remove proton from this oxygen and it will generate a enolate here. Because this is acidic proton, it will also be removed, and we have one acidic proton here, two acidic protons are here, so it will remove any one of them and it will generate an enolate. That is why we are using more than one equivalent of this LHMDS here in this reaction. Then if I am using methyl iodide, suppose, then this methyl group will attach from the side above the plane, the side opposite of this OLI. This chiral auxiliary decides the attachment side of incoming methyl group, and in this reaction we are preferentially getting this cis, so we can remove this chiral auxiliary and we will get this alpha amino acid, right? So this way is much simpler than this one, but you should know the mechanism of both of them, right? Then we will take asymmetric conjugate addition reaction of carbonyl compounds. So in this reaction we are using a simple amine here, right? And you will see that this simple amine can act as a good chiral auxiliary. So how we can generate chiral auxiliary? First we have to treat this with this carbonyl compound, so it will form a imine, right? First it will form imine, and we can also write it down like this, right? Next we are using a alpha beta unsaturated carbonyl, so it will show conjugate addition reaction. So you can write down it like this. The most important thing is this amine, this simple amine is acting as a chiral auxiliary, right? So sometimes you will not look at this thing that it may also act as a chiral auxiliary, so that is why this reaction is important. So the reaction will be like this bond will shift here and then it will attack on this carbon because it will show conjugate addition, so it will attack like this. But the important thing is the attachment side of this group. So because this methyl group is on the below the plane side, that is why this group will attach on above the plane. So this chiral auxiliary decides the attachment side of this alpha beta unsaturated ester, and this methyl will go below the plane. Then we can do hydrolysis to remove this imine group, right? And we can again generate this carbonyl compound. So this reaction is very simple and very important. Then we will take a very important reaction. Again, this is very important, that asymmetric induction with Lewis acid having chiral ligands. So we have here a Lewis acid which has chiral ligands. This lithium aluminium salt has chiral ligand, this binol. This is the structure of this lithium aluminium salt of binol. So due to these rings, it has chirality, right? Because they will show they are in different planes and they have atrop isomerism due to these bonds. That is why these ligands are chiral in nature. Asymmetric induction and this Lewis acid, this lithium aluminium salts, causes conjugate addition. This is very important point because now you know that they will induce chirality in the reaction. But next question comes that the enolate generated from this 1,1,3-dicarbonyl compound will attack directly on this carbon, or it will show conjugate addition. So when we have lithium aluminium salt, it will show conjugate addition, right? So in this reaction we will get this product with greater than 99% enantiomeric acid. Next and very important part is aldol condensation with chiral auxiliary. So we know that this part is our chiral auxiliary and we can easily generate enolates from this reaction, and we can also attach group on it, right? So in this reaction is combination of two things we have studied so far. That we have studied that we can use different boron reagents to generate enolates, and second thing is use of chiral auxiliary. So here we are using a boron reagent which have smaller size ligands. These ligands are small in size and it has good leaving group, right? And we have here hindered amine, right? In all these three conditions will give us cis enolate, right? Smaller size ligand, good leaving group, hindered tertiary amine. So all these conditions will give me cis enolate, means we will preferentially have this type of enolate. So first part is salt, second part is attachment side of this PHO, this PHCHO, right? So it is our aldol condensation reaction, simple, that this bond will shift here, this bond should be here, right? And it will shift here, then this will attack on this carbon and it will form OH. So we know that we have generated here cis enolate, and this cis enolate we have generated here cis enolate, and we know that this cis enolate will give us syn aldol. Syn aldol means we will get a product like this, that suppose my OH is on the above the plane side, then this methyl group, this one, should also be on the above the plane side, and rest part will remain as such. Now what is the use of this chiral auxiliary? So we know that it will give us syn aldol. Syn aldol means these two groups should be on the same side. So they can be above the plane, they can be below the plane. Both conditions are syn, but because this group is on the below the plane side, that is why these two groups will attach above the plane, and this is also our syn condition, right? That is why this reaction is very important. So you have to remember first that which type of enolate you are generating. Either it is cis enolate or trans enolate. Cis enolate will give you syn aldol and trans enolate will give you anti aldol. Next question comes that which type of chiral auxiliary we have. This chiral auxiliary will decide the attachment side of these two groups. Next reaction is asymmetric boron mediated aldol condensation. So we have used different boron reagents in previous reaction. This time we have diisophenol camphenyl boron triplet, IPCBO triplet. So we can have minus IPC or we can have plus, right? Both of these will give us syn aldol product. Means first they will give cis enolate and then these cis enolate will give us syn aldol product. So remember the case of this reagent also. Sometimes you can think that because it is bulkier in size, so it will give us trans enolate, but remember the case of IPC where you will preferentially get cis enolate and then it will give you syn aldol. Now you can easily do this reaction. First we have to generate a cis enolate, then this cis enolate will attack on this aldehyde. It will not attack on this carbon, it will attack on this carbonyl group directly. So this is all about asymmetric aldol condensation reaction. In next chapter we will take different lithium reagents, right? So keep watching, and if you like my videos, please share my videos with your friend. Thank you so much.